Okay, we're ready to talk about the identity matrix and the inverse of a matrix. Okay, so this is very important. The identity matrix is pretty simple. The identity matrix, we use the letter I to denote, and it's a square matrix, so it has the same number of rows as columns. It has ones along the main diagonal and zeros everywhere else. Here's some examples: the 1 by 1, 2 by 2, 3 by 3. Along that main diagonal, remember the main diagonal entries are where the row and column number are the same. So 1, 1, 2, 2, 3, 3. Those have ones. Anywhere where I and j are not equal are 0. So here's a way we can write it out. Remember ijth entry, I is the row number, j is the column number. So it's a 1 if I equals j and a 0 if I is not equal to j. And so this is the identity matrix. And look at this property. If I have the matrix A and I multiply by the identity matrix on the left, notice since it's 2 by 3, I'm going to need the 2 by 2 matrix to do that, right? So this is 2 by 2, and this is 2 by 3. So I can do the multiplication. The inner numbers are equal, all right? The outer numbers, 2, 3, give me the size of the resulting matrix. And look what happens. When I do row times column, each time this 1 is going to pick off the top row entry. This 0 down here is going to zero it out. So I'm going to get a 2. 1 0 times 3 0 is 3. 1 0 times negative 1 8 is negative 1. And then with the second row, notice it's going to pick off the entries in that bottom row, right? And what do we get? We get back to the original matrix. If I do A times I, in this case, right, A is 2 by 3, I'm going to need the 3 by 3, right, identity matrix, because I need these middle numbers to match. And you do this row with this column, this row with this column, this row with this column. That's going to give you these entries here, right? And then this row with this column, this row with this column, this row with this column gives you this row here. And we get back to A. So what's the idea? The identity matrix is like the number 1 for real numbers. If you multiply a matrix, any matrix, by the identity matrix, you get the matrix back, essentially. Okay. A lot of times you'll see the subscript n or m for the size of the identity matrix, but a lot of times we'll just leave it off, implying that the matrix I has to be of the size needed if you're doing multiplication or addition or whatever. Okay, so that's the introduction of the identity matrix. And before I talk about the inverse of a matrix, which is really what we want to get into, just one quick thing to talk about, this little short theorem. This kind of ties it into something we've talked about before. If R is the reduced row echelon form, you remember what reduced row echelon form I hope is, of a square matrix A, so it's a square, n by n, has to be square, then this matrix R, this reduced row echelon form of A, either has a row of zeros or it's the identity matrix. Those are the only possibilities. There's two things. And let me just show you, one possibility certainly is this, right? If I have the n by n matrix where I have ones all down the main diagonals, zeros everywhere else, that is going to be the identity matrix. Okay, so just dot 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 pattern continues, right? So ones all down the main diagonal. So if this is an n by n matrix, this is certainly reduced row echelon form, right? Each row, the first non-zero entry is a 1, so we get our leading ones. They're in echelon form, right? The leading one here is going to be to the right, right? And so on. Each time we'll go down to the right. It's in echelon. And every leading one has zeros everywhere else. So it's reduced, right? So this is reduced row echelon form, okay? But what else could happen? It could be that instead of the 1 being here, sometimes what happens, it gets pushed further to the right. So there might be a 0 here, and this leading one, it gets pushed further to the right. That can happen. Well, if this leading one gets pushed to the right, then the leading one here has to get pushed further to the right. And the leading one in the next row has to get pushed. All the way down till we get to this leading one, what happens? It's going to have to be pushed out, so to speak. And you are going to have guaranteed, what, a row of zeros, at least one, right? So that's what's possible. You're either going to have the identity matrix or you have to have a row of zeros. Okay, and we'll use that idea later on. Okay, so that was just sort of tie in something with what we've talked about before with this new identity matrix. Okay, so now we're ready to talk about the inverse. Very, very important. In fact, the whole course will be focused, really revolve, if you will, about this idea. Let A be a square matrix. Okay, so we're talking about square matrices only here. Very important. If we don't have a square matrix, we can't talk about an inverse. So if A is a square matrix, if B is a same size square matrix, right, and that matrix B has the following property. If I do A times B, that's the same as B times A. Now that's an important step because we just said in the last video, this in general is not true, right? Matrix multiplication is not commutative. But there are some matrices that do commute. And so B is such a matrix, right? B and A being both the same size. But not only that do they commute, but their product is the identity matrix. Okay? If we can find a matrix B that does that, at least one, then A is said to be invertible or non-singular. So you'll need to know this definition. Invertible and non-singular mean the same thing. And this matrix B is what we call an inverse of the matrix A. It's an inverse. When we think of inverse, I want you to think about like the reciprocal of a real number. That's sort of the analogy, right? What's the reciprocal of 3? 1/3. What do you do when you multiply 3 times 1/3? You get 1, right? Here's a similar thing where we're multiplying to get the identity. It's important to note we don't have a defined division involving matrices. We have matrix multiplication, right? Addition, scalar multiplication, but we don't have any division. But this essentially is what we're going to do in division instead, is think about the inverse. Okay? If no such matrix B can be found, if there's no way for us to find for a given matrix A multiplied together to get the identity matrix, then A is said to be singular or non-invertible. Clearly the zero matrix that we talked about in the last video, the zero matrix, a square matrix with all zeros, is going to be singular. I can't multiply the zero matrix by anything and get the identity matrix. But here's the thing. There are many, infinitely many non-zero matrices also that are singular. And that's different because real numbers, 0 is the only number that doesn't have a reciprocal, right? 0, we can't multiply 0 by anything and get 1. Every other real number we can. So we only have one sort of singular real number. But for matrices, there are infinitely many singular matrices of different sizes. Okay, 2 by 2 really and above. Now, I'm going to prove this theorem. It won't be as bad as the proof we did in the last video. It'll be a little bit shorter, but it's a very important one, and it's essentially the uniqueness of an inverse. So here's the theorem. If B and C are inverses of A, right, so they behave this way when we multiply A on the right or left, we get the identity matrix, then B equals C. In other words, what this is saying is that if A is invertible, there is only there's a unique, if you will, inverse matrix. Okay, there's a unique inverse, and it's not clear at all that that's the case from this definition. We don't know. I mean, we already know matrix multiplication is a little screwy because we can't commute in general, and in this case we can. So how does this work? For real numbers, we have certainly unique inverses, if you will, or reciprocals, right? As I said, the reciprocal of 3 is 1/3. And they come in pairs, right? Obviously the reciprocal of 1/3 is 3. Well, that's also true for matrices, but we have to prove it. Okay, so here's the proof, and this is a sort of classic proof that I would like you to be able to do. So what I'm going to start with is the fact B and C are both inverses of A. So let's start with B. B is an inverse of the matrix A. All right. So what's that mean? So that means, well, a couple things, but I'm just going to use this fact that B times A, if I multiply B times A, I get the identity matrix. Also, if I multiply AB, right, same thing. But B times A, I get the identity matrix, right? Okay? All right. So what I'm going to do now is I'm going to multiply by C on the right. Keep in mind, since we're talking about B and C both being inverses of A, they all have to be square matrices of the same size. So matrix multiplication is always defined, right? So I'm going to multiply this equation by C on the right. And it's real important that I do it on the right, as you'll see here in a minute. So on the right, so BA times C over here. All right, so BA times C over here equals I times C. Now, so I'm multiplying by C on both sides, right? And what do you know about I times C? What did we just say up here? Whenever I multiply any matrix by the identity, what do I get? I get back the original matrix, right? So I times C is just like 1 times a real number. I times C is just C. Okay? But here I have, therefore, BA times C equals C. Okay? Remember, I cannot change the order over here. So in other words, BAC is not ABC or BCA or anything like that. I can't commute in general, but I can regroup. I can regroup. In other words, I can rewrite this as BAC, right? Now, why would I want to do that? Well, notice AC, if I multiply that first, what do I get? Well, C, we said B was an inverse of A, but C is also an inverse of A. And this is the identity then. This is true since C is an inverse of A also, right? So I'm using both the facts that B is an inverse of A here, and then here I'm using the fact that C is an inverse of A. But what's B times I? B times I is B, right? B times I is B, and we get B is equal to C. And therefore, you know, we're done because that's what we had to prove, right? So if B and C are inverses of A, then B equals C. So it's important that we have to prove this. We just can't say, well, they're obviously equal. You just can't say that, right? You have to prove it. And notice I don't even talk about giving examples of matrices. You can certainly give examples where this works, but we're not doing examples where we're proving the actual theorem. Okay, so I'd like you to be able to prove that theorem doing something very similar to what I've just done. Pretty short. Now that we know inverses are unique, we are going to give them a specific notation, if you will. And so here is the notation. The inverse of a matrix A is going to be denoted A with a superscript -1. Okay? And this is a universal notation for an inverse. I want you to realize that for real numbers, when we see the -1 as an exponent, that means the reciprocal, right? 3 to the -1 power is 1/3. But this is not a power in that sense, right? Because this is not 1 divided by A. That doesn't make any sense. We don't divide by matrices. Okay? It's the notation. In fact, we say A inverse. We pronounce this A inverse for short. Inverse of A or A inverse. Okay? And so if I multiply A and A inverse together in any order, I get the identity matrix. Okay, so what I want to look at first of all is I want to give you a formula for finding the inverse for a 2 by 2 invertible matrix. So if a matrix is invertible, if it has an inverse, then here is a formula for you. All right? For A given this general matrix, and instead of doing the double subscript notation, make it easy, we just do A, B, C, D, okay? Then the inverse is this quantity here, which is a scalar, right? Remember, A, B, C, and D are scalars. And then a scalar multiple of this matrix. And kind of see the relationship between this matrix here and this one. The B and C kind of what? They change sign, but they stay where they are. The A and D kind of swap. And then you still have to multiply by this. So there's a little bit of a thing going on. We'll show you later on a more general form for the inverse for an n by n matrix later on in the course. But that's a real big problem, is finding inverse, especially for very large matrices. I'm going to prove this formula works, and the proof is straightforward. Anytime you want to prove, if I give you a matrix A and I say this is its inverse, how do you prove it? You simply multiply the two matrices together and make sure you get the identity. So I'm going to do A inverse times A. Okay, so A inverse is 1 over AD minus BC, D minus B minus CA, and of course A is the matrix A, B, C, D. And I'm going to multiply the matrices together, and then I'll scalar multiply. Okay. Okay. So what do I have? 2 by 2 times 2 by 2 gives me a 2 by 2. So notice I do the first row dotted with the first column. D times A is AD, minus B times C is negative BC, so plus and negative BC or minus BC. So there's the first row dotted with the first column. That's my first row, first column metric. First row, second column, first row, second column. D times B is BD, negative B times D is negative BD. What happens there? Right. That's going to be a grand total of 0, right? So that's nice. That will equal 0. And then we go down to the second row, first column. Second row, first column. I get negative AC plus AC. Well, that's also going to be 0. Well, that's nice. This entry is also 0. And then what do I get here? I get, second row, second column. Negative BC plus AD. I get negative BC plus AD. But notice that negative BC plus AD is the same thing as AD minus BC, isn't it? And so notice, when I multiply by 1 over AD minus BC times this entry, what do I get? I get 1. Right? Same thing here, I get 1 here. So scalar multiply, everything gets multiplied. Of course, the ones I multiply 0 by anything, I get 0. And so the end result is what? I get the identity matrix. Okay? And similarly, you can show, I'll let you show that A times A inverse is also the identity. It doesn't matter the order you multiply those in. Okay? And that's the proof of that formula. So that formula works. Now, look at that formula. Under what circumstances would a matrix A be invertible? You know, we said that not all matrices are invertible. Well, in particular, this tells us for 2 by 2 matrices, we can tell something, given the entries A, B, C, D. Look here, this scalar amount would be undefined if what? AD minus BC were what? Equal to 0, right? So in other words, if you have a matrix A, B, C, D, right, 2 by 2, it's invertible if AD minus BC is what? Not equal to 0. Right? So that quantity cannot be 0. And that's an important quantity. We're going to talk about that quantity a little bit later on in the course. Okay? But now that we have a formula, let's just use it. Okay? And I'm going to show you then after that an example of how the inverse is the power, one of the powers of the inverse. Look at this matrix A here. Okay? And let's take a look. So you know, think about this formula that we just had, right? A, B, C, D. So let's look at AD minus BC and make sure it's not 0. So we can show it, first of all, it has an inverse. A is 2. D is 2. It's got AD minus BC. B is negative 3, right? And C is 1. So I get 4 minus a negative 3. 4 minus a negative 3 is 7, which is not equal to 0. So it's invertible. Right? It's invertible. And what is the inverse? Well, it's 1 over AD minus BC, which we just said is 7, so it's 1/7. And then look how we change things. The A and D get sort of swapped. Well, in this case, it's just 2 and 2. And then these change sign, basically. This becomes -1, this becomes +3. And so our resulting matrix is 1/7 times 2, which is 2/7. And then just scalar multiply all of these by 1/7. Okay. So there's your inverse. And you can check and verify this. Let me show you real quick in the calculator. We do have a way. Let me go to matrix. Let me go over and edit this 2 by 2 matrix. And I'm just going to do this one, 2, -3, 1, 2. Okay, there's that matrix A. And we'll get out of that. And now if I go to matrix and do matrix A, and right here, matrix key, x to the -1 power, like you would do reciprocal. If I hit that, it does a -1 exponent. Since that's a matrix, the calculator interprets that as the inverse. Okay, since my inverse has fractions, I'm going to go to Math and do Convert to Fractions. And if I do that, indeed I get the same thing. Okay, so your calculator will find inverses for you. Also, if it's not invertible, it will say error, singular matrix. So it will say singular matrix is error. So it'll tell you. But again, we're not just going to be button pushers. We want to know, how does the calculator do that specifically for larger, 3 by 3, 4 by 4, and so on. That's something that we're going to be exploring in shortly, in a little while. Not in this video. But let me just show you a nice little useful thing for this. Remember, let's go back to systems of linear equations, and they're interrelated with matrices we know. In fact, we saw how to write this system as AX equal B in the last set of lecture videos. Do you remember that? A is the coefficient matrix, which is 2, -3, 1, 2. X is the variables matrix. In this case, I've just got X and Y. And B is the constants. Right, so I can express this equation as this matrix equation. So if I multiply A times X, I'm going to get this matrix here, right? And so notice this A is the same A that I have here, okay? So this matrix is invertible. So what I'm going to say, I'm going to multiply by, this matrix equation, I'm going to multiply by A inverse on the left of both sides, right? Since both sides are equal, I'm going to multiply by A inverse, and I can do that because AX and B are both sides what? 2 by 1. And so A inverse is 2 by 2, and I can do that multiplication. All right, so what I'm going to do here is I'm going to regroup, though. I'm multiplying A inverse times A times X. I'm going to regroup. This is A inverse times A. That's a property that we saw last video for matrices. I can regroup, reassociate, multiplication. I can't rearrange, can't commute anything. Over here I just have A inverse B. But what happens here? What is A inverse times A? A inverse times A, that's the identity, right? When I multiply a matrix by its inverse, I get the identity. And what's I times X? It's just X. And you see what we have? We have a solution. We have the values of X and Y here. It's A inverse times B. And so this is a matrix method for solving a system. Now it only works if we're talking about a square system, meaning we have the same number of equations as unknowns, so that our coefficient matrix is square. And what? This matrix has to be invertible. Okay? What's the inverse? Well, we just found it up here, so I'm just going to copy that matrix down here. And multiply it by B, which was 5, 6. All right, this one right here. Copied it down there. So 2 by 2 times a 2 by 1 gives me a 2 by 1. And the first entry is what? The row dotted column. 2 sevenths times 5 is 10 sevenths. 3 sevenths times 6 is 18 sevenths. So 10 plus 18 is 28 sevenths, which is 4. -5 sevenths and 12 sevenths is 7 sevenths, or 1. And so this tells me my solution, right? Remember the X was what? XY. So X is 4 and Y is 1. So this is another way you can solve a system by matrix multiplication. We were looking at solving matrices using Gaussian elimination, right? But this is another way for a square matrix, for a square system rather, where the coefficient matrix is square and invertible. We can use this nice technique. So that's one use of the inverse. Okay, so we're going to, in the next video, take a little bit more in-depth look at the inverse matrix and properties involving it.